There is constant heat transfer in the environment. Heat flows from hot to cold. To be more precise, when a hot object is brought into thermal contact with a cold object, heat flows from the hot object to the cold object. The cold object gets hotter, and both reach some equilibrium temperature, which is in between the two starting temperatures. The final state, where the two objects have the same temperature, is known as thermal equilibrium. In this video, we will talk about the three ways of thermal contact: conduction, convection, and radiation. Conduction involves the interaction of adjacent particles with the material. Conduction occurs in solids and fluids. Different materials transfer heat by conduction at different rates. This is measured by the material's thermal conductivity. So how do we know this? The following experiment would demonstrate the thermal conductivity of different metals. An equipment is set up with 5 different metals. Attach 2 pins to each rod with a small lump of Vaseline. Pour boiling water into the equipment. The metals are bronze, steel, copper, zinc, and aluminium. When the metals are heated, atoms start vibrating. As the metals get hotter, the atoms vibrate more vigorously and have more kinetic energy. Metals are good conductors because they have electrons that can move about freely. They carry the energy through a metal as vibration is spread. As the heat is transferred, Vaseline is melted, causing the pins to fall. The faster the pins fall, the faster the conduction and the better conductor the metal is. So now, as we know, out of the 5 metals, aluminium is the best conductor while steel is the worst. Metallic solids are good conductors while most non-metallic solids, liquids and gases are poor conductors, also known as insulators. A metal frying pan is an example of a good conductor. If you touch the metal part, you will notice it's very hot. That is why the frying pan handles are made out of wood to better insulate the heat. Almost everyone has heard the meaning of the saying hot air rises, but what exactly is convection? The following experiment will demonstrate the process of convection. A convection tube filled with water is clamped to a tripod. A Bunsen burner is set at one corner of the convection tube. At the top of the tube, place a tiny pinch of powdered potassium manganate and watch what happens. At the corner of the convection tube, water is heated. The particles in hotter fluid move around faster because they have more kinetic energy. At the same time, they expand and the same amount of particles take up more space. Therefore, the fluid becomes less dense than the surrounding and rises into the colder areas where denser fluid falls into warmer areas. This way, a convection current is formed. This is what's being shown by the convection tube. Some examples of convections are heaters, boiling water in a pan, wind currents, and the Earth's mantle. All objects give out and take in thermal radiation. For most bodies on Earth, this radiation lies in the infrared region of the electromagnetic spectrum. Unlike the processes of conduction and convection, thermal radiation can move into empty space without requiring an intervening medium and can take place in a vacuum. This is why we can still feel the heat of the sun, although it is 150 million kilometers away from the Earth. All bodies are able to emit and absorb thermal energy in the form of infrared rays. When the absorption of energy is greater than the emission of energy, the temperature of the object rises. If the absorption of energy is less than the emission of energy, the temperature of the object falls. When the absorption of energy balances the emission of energy, the temperature of the object stays constant. The rate of infrared radiation is mostly affected by 3 factors. The following experiment will show one of these factors. Set up an apparatus like this, a radiant heater and 2 cups equidistant to it. As shown, one cup is in black in color and the other silver. The two are the same size and made of the same material. The cups are filled with the same amount. The radiant heater is turned on. After 10 minutes, the thermometers have recorded the cup's changes in temperature. The water in the black cup is now 26 degrees, and the water in the silver cup is now 23 degrees. This shows the color of the object affects the rate of infrared radiation. Dark and dull surfaces are good emitters and absorbers of infrared radiation. Light and silver surfaces are poor emitters and absorbers, but good reflectors. The surface area also affects the rate. The larger the surface area, the better emitter and absorber the object is. The third factor is temperature. Objects with higher temperatures usually emit and absorb more thermal energy. Overall, if the object is a good emitter of radiation, then it's also a good absorber. This is why on a hot sunny day, the black plastic parts of cars become very hot, and the sunshield drivers use usually white and shiny as it helps reflect away light and infrared radiation. The three types of heat transfer, conduction, convection and radiation, happen all around us. A vacuum flask is a good application to show all three types of heat transfer. The vacuum between the double layer prevents heat transfer from conduction and convection. The silver coating reduces heat transfer from radiation. Lastly, the stopper prevents convection current from forming. The study of heat transfer provides economical and efficient solutions for critical problems.